Recording's rolling. It is Thursday, September 25th. We're going to take all class period to do some textbook puzzles. I put these in your hands a few days ago. Chapter 4 or 5 dynamics. Next Friday. Yeah, there's a lot of these. Yeah, so not for at least a week. There's a lot of these, so I might narrow this down or probably not. How do you guys do all of these? I mean, let's do like one. You can do all of them. You guys should practice, right? But we'll do as many as we can class today, and then I'll see how it pieces out over the next few days. Right, last few days, you guys been doing Christian and Atwood labs, and we did a debrief yesterday also. So have those turned in. So we had turned them in yesterday. So we guys turn them right now. I'll be getting those in the grade book fast again. Right, so my plan with these puzzles is to do the first few together with you guys, like this first set right here. And so those are some good warm ups. Get the basic principles. Okay, and then I did go through and I highlighted ones that look like the labs guys did last couple days. So like there's an Atwoody looking one. It's a different Atwood setup. There's like a friction one looking here. I got some frictions in Atwoods. And we won't have enough time this class period to do all of those, but maybe some of those. Okay. And so sorry, the beginning here. And the numbering is weird, so the numbers don't really make any sense. Like 3, 4, 5, and then it skips back to number 6 or something, but right, whatever. So some of these first ones came out of chapter 4. Number 3, first one I picked here. The net force on a moving object suddenly becomes 0 and remains 0. That object will, so maybe this object had a force or forces on it, but then maybe the net force goes to 0. So there might still be forces, they just come to 0. But here, to give you guys a picture, here, that could just be anything in equilibrium. Right? Isn't that one of the setups from last few days? So maybe that happens. Right? That happens right there. Right, what will the object do? Right, let's read the answer, then I'll see show of hands. Will 0 net force, will that stop abruptly? Will it reduce speed abruptly? Will it reduce speed gradually? Or will it continue to move at constant velocity? Right, you guys have the premise, right, in the options. Okay, show of hands. How many guys think 0 net force means it stops abruptly? Who says that? Who says 0 net force reduce speed abruptly? Who says 0 net force reduce speed gradually? And who says 0 net force will continue to move at constant velocity? Oh yeah, there's all the hands right there. Oh, look at all those winners. Yeah, because 0 net force just means, well, goes hand in hand with 0 acceleration. Okay? You can still have motion, but you just can't be speeding up or slowing down. Because if you were speeding up or slowing down, that would mean that there would be a net force. Okay. Number 4, in the absence of a net force, an object cannot. Right, now this one tripped me up a little bit just because it's like a double negative. Right, so let's slow down. Okay, when it says absence of a net force, guys, could that right there be absence of a net force? Yeah, because there are forces, but they cancel out horizontally, they can cancel out vertically. So this is absence of a net force. So what can this not be doing? Okay, you guys get that? What can this picture not be doing?
Remaining at rest.
Can it not remain at rest?
It cannot remain at rest.
Can it not be in motion at constant velocity? Can it not be accelerating? Or it cannot be displaced of like it's moving? Okay.
Oh wait, it's
Guys, can this be at rest?
yeah.
Yeah, if this was static friction, then it could be at rest. It would look like a same Petri bond diagram. Right, so the answer is not A. Guys, could this be in motion at constant velocity? Yeah, no, this would of course be kinetic friction at that point, but that's what the title of this is, right? Constant velocity. Guys, could option C, can this be accelerating? No. You're right, it cannot be. So that's the answer. This cannot be accelerating because there's no net force. You guys have that? Right, number 5. According to Newton's second law of motion. Here, Newton's second law. Anyway, I know that's one of the posters I have ready to go.
So net force just
here it is.
If it's not,
okay. All right, so guys, recap. Newton's second law of motion tells you how something accelerates. So the acceleration is proportional to the net, or I should say directly proportional to the net force. So guys, if you triple the net force, do you triple the acceleration? Yep. Okay. But also, the acceleration is inversely proportional to the mass. So guys, if you triple the mass, what happens to the acceleration? It's 1/3 as much. It's smaller, doesn't it? Okay. What's the options here? Newton's second law of motion. When a net force is exerted on an object, its acceleration is acceleration inversely proportional to the object's mass? Yeah, sure is. Right? Option B says independent of the object's mass. Right? What does option B mean? If something's independent, yeah, that would be no relationship. So I can do a quick demo to show you the difference between these two. Okay? So it's basically got a small object and a large object, and I put the same force on both of them. Force on the small object, that's huge acceleration. Same force on the big one, okay. It's hard to move it at all. Right? So same force, different objects. Yeah, smaller mass accelerates a lot, and vice versa. Okay? See, if it was independent, what that would mean is the same force on these would accelerate them both the same. And okay, that can't be true. That's not true. All right. All right. Numbers. Yeah, let's do 7, 8, and 9 right here. So number 7, what net force would be needed to exert would need to be exerted on a 2 times 10 to the 3 kilogram car to accelerate it at 4 meters per second squared. I'm going to draw that one up. Okay, so number 7. Okay. So if you got we're actually going to do an extension question on those two.
Number 5.
Oh, yeah. Number 5 is, according to Newton's second law of motion, when a net force is exerted on the object, that acceleration is inversely proportional to the mass. That's number 5. Inversely proportional to the mass. Right? So number 7, let's get a car going. Okay. Wait, was I thinking of this one or?
Oh wait, what's number 4?
Okay, number 4. In the absence of a net force, an object cannot be accelerating. Right? So if there is acceleration, there must be a net force. And if there's no net force, there's no acceleration. Okay, so number 7, you're given, it says net force on number 7. F net is 2 point, no, I'm so sorry. Sorry, we don't know. So the mass of the car is 2.00 times 10 to the 3 kilograms. So they gave you that. Right, that's given. Also, they gave you the necessary acceleration is 4.00 meters per second squared. Right, so here's your givens right here. And we got to figure out something about net force. Okay. All right, so here's my car. Maybe the car is trying to do force, so I'll give it a forward velocity, although that's not part of the free body diagram. Okay. But let's make a free body diagram. Okay. So we're doing a little lecture on this one. Guys, you can tell me, what is the weight of this car equal to? mg. Okay. And if the mass is, guys, how many kilograms is this just as a plain number?
2,000.
Yeah, 2,000 kilograms. You guys see that's a 2,000 kilogram car? Right? That's true? Right. Because 10 to the 3. Now, the disadvantage of writing it as a plain number is you don't know how many digits are significant. It's kind of ambiguous. Right? But in scientific notation, you know it's exactly 3. Right? The last physics textbook that we used for the last 10 years also tended to make every given number 3 significant digits. So the sixth one's the idea. Okay. Here, I'll give you guys something else. Let's just call gravity 10 meters per second squared. Okay. So we can round a little bit. And if that is true, put this all together. How much does this car weigh? Guys, is weight in kilograms or newtons? Weight is in newtons. Weight's a type of force. Hence the vector. mg, 2,000 kilograms, 10 meters per second squared. That 20,000 newtons, right? 20,000 newtons. If I write out the number long form, it looks like that. Okay. Okay. And guys, what force is holding the car up?
Normal force.
Normal force, which is how many newtons?
20,000.
20,000 newtons. Okay. As long as it's a level road, I think it's a fair assumption, right? That it's just a horizontal road. Okay. Okay. Now, suppose the car starts at rest, and we're trying to get this car to accelerate forwards at 4 meters per second squared. Guys, which direction would the net force be acting on it? If it's accelerating forward, the net force must be which way? Also forwards. Yeah, also forwards. Right? So I'm just going to label this force right now, like some ambiguous force, and we'll come back and address what kind of force we talk about. But numerically, isn't it just net force equals mass times acceleration straight from Newton's second law of motion? Okay. So we got a 2,000 kilogram car. We're trying to accelerate it at 4 meters per second squared. So put that together. Would that be 8,000 newtons? Is that true? 8,000 newtons? Okay, guys got that? Okay. So I think that would be this force right here. Could be 8,000 newtons, right? Okay. And that would be the net force. There are 3 forces. The 2 verticals cancel. The force you're left with is the horizontal force. And that would be 8,000 newtons. Right? Sure. All right. Now, next question though. What type of force is that though? That's a what kind of force? It's not a tension, it's a what? Not a weight. What force is actually pushing it to the side?
Yeah.
Friction. Guys, that right there is a friction force, right? Here, how about a counterexample? What if the road was like either iced over, or what if the car is sitting in a mud pit and the wheels are just spinning in place? Ooh, is that car not even moving at all? Because there's no friction to get it going. Yeah, because there has to be traction between the tires and the road to force the car forward. Actually, I should have drawn the wheels bigger. Let's get some bigger wheels. Okay. Right. Yeah, guys, isn't friction always sort of like opposed motion? Right? Try to oppose motion. Right? Now, um, if you consider how the wheel is turning, here, if I blow up the wheel, right, let's zoom in on this wheel right here. Here's the wheel. Right, here's like the front of the car. I'm like zoomed way in, right? Right? Isn't the wheel trying to turn like this? I say the wheel's trying to turn like that, right? And now the center of the wheel is just moving along with the car, has the same speed as the car, right? The top of the wheel is actually moving twice as fast as the car relative to, say, a nearby tree. So if the car is going 60 miles an hour, the top of the wheel is going 120 miles an hour. Okay? But the bottom of the wheel is actually instantaneously, moment by moment, not moving relative to the road. Okay? In fact, relative to the car, isn't it moving backwards? Yeah, right. So the tire is sort of like trying to move backwards relative to the car on the underside, like on the bottom side. Okay? And because friction acts opposite motion, that propels the car forward. So now that car is able to move forward. Yeah.
Why is the weight 20,000 and not 2,000?
Okay, because the mass was 2,000 kilograms. And you put that in Earth's gravity of 10 meters per second squared, that's a 20,000 Newton weight.
Do we
Okay.
turn in our lab?
Yeah, you turn the lab. Yeah, got Rachel up here. You know what? So, guys, remember the difference between mass and weight. Okay, would this car out in deep space just floating around still have a mass of 2,000 kilograms? Yeah, if you were an astronaut and you came across and pushed it, look, you would feel sort of like 2,000 kilograms worth of inertia, like resistance to change in motion, right? Okay. But weight's a different concept. Weight's not a scalar. Weight's a vector. Weight's pulling straight down. Right? So this weighs so many newtons. It has so many kilograms of mass. That's inertia, and so many newtons of weight that's pulling straight down. Okay. Yeah.
All cars keep driving on the so the wheels are going backwards.
Yeah, like okay, yeah, back to this wheel. Yeah, if you're sitting inside the car, you're saying what's the motion of the wheel relative to you? Well, all different points on the wheel are doing different things. Like the center of the wheel is not moving relative to you. The top of the wheel is actually moving pretty fast in the forward direction. And the bottom of the wheel is actually moving backwards relative to you sitting inside the car. The circle turns, yeah, because the wheel's turning. Right? Okay. Okay. So that's relative to you inside the car. Right?
So the friction will be in the same direction as the velocity. Because...
Right. So the friction is pushing the car forward. Yeah, and that's what's propelling the car forward. Right. Right. See if there was no friction, if the road was iced over, or if the car was in a muddy pit, those wheels might just be spinning, boom, and the car doesn't even move anywhere because it's gaining no traction. Like traction would be friction. Yeah. Okay. But if you give it, say, a coefficient of friction between the tires of the road, now that would propel the car forward. Okay. So it's a friction force actually driving the car forward. Okay. Right. And here's my other follow-up question is, what is the minimum coefficient of, would this be a static or a kinetic friction case? You're trying to gain traction and propel the car forward. Static. Yes, static. Right? Because the wheel's trying to push against the road. Right? Say if it was spinning like burned rubber, that would be kinetic. But the coefficient of static friction, static friction between the tires and the road. Right, so there's my extension question right there. Right. So how could you solve for that? That's something related to this, right? Something related to this. Right. Go ahead. Okay, so somebody calculate what is the minimum coefficient of static friction? And when you get it, raise your hand. All right, who figured it out? Who knows the minimum coefficient of static friction? That's me sub s. Between the tires of the road for this scenario. Who knows it? Who figured it out? Okay, I'll walk you guys through.
Wait.
Oh, yeah. Minimum coefficient of static friction. Okay? Because I think if the road was iced over, there might be not enough friction for the car to even accelerate it 4 meters per second squared, which was a good value. Okay? So it has to be some minimal value, right? Okay, the road's probably not iced over. Okay. Looking for one more post. Okay, I have it here. Okay. While you guys are thinking of that, here, one more shot here. Okay. Do you guys remember these coefficients of friction here? These coefficients of friction, right? Between tires and different kinds of roads. We got a icy road, wet road, dry road. We got these different coefficients of static friction. Right? I think if this was an icy road, it would be not even enough friction to allow the car to accelerate as much as you want it to. Right? Okay. Guys, all you need is this pink box right here. Guys, in place of the friction force, put 8,000 newtons. Okay, so mu s should be greater than or equal to friction force compared to normal force. Isn't that coefficient of friction? Okay, friction force compared to normal force. Okay. In this case, the friction force, well, we determined that has to be 8,000 newtons. And the normal force is how much? 20,000 newtons. 0.4. Okay. Now, it could be more than that. Like if the coefficient of friction was like 0.9, it could definitely accelerate at 4 meters per second squared. Okay? If it is 0.4, it can just barely, okay, so the wheels are just about slipping, you just barely accelerate it that much. Okay? What if the coefficient of friction was like 0.1? Would the car be able to accelerate that much? No, not anymore. Okay, guess that. All right, ready for the next one? Squat. Huh?
With the greater than or equal to, is that an M?
This is mu. This is coefficient of friction mu. Okay. Okay. The coefficient of friction ratio of friction force to normal force. Okay. Yeah. All right.
Equal one? Oh, that's 20,000.
Yeah. All right. Let's do number 8. It says two forces, magnitudes 30 newtons and 70 newtons, are exerted on an object. What's the minimum and maximum values of the magnitude of the sum of the forces? Now, when I say the sum of the forces, keep in mind forces, of course, vectors, so they could have any spatial direction. Okay. So let's come up with a bunch of combinations. Oh, I'm going to draw this out. Number 8. So, guys, could you have 70 newtons and 30 newtons acting in the same direction on an object, right? But suppose that's my object right there. And pushing with 70 and 30 both to the right. This would be 70 newtons plus an additional 30 newtons like that. That'd be correct. Now, if I drew that as a free body diagram, I would do center mass dot. I would do 70 newtons like this, and then 30 newtons like this. Right? But if I'm adding them together, guys, can I add those tip to tail? You guys remember tip to tail vector addition? Okay. Here's a reminder of tip to tail vector addition. Suppose this object right here, bam, has these 5 forces on it. So it looks like you can see it at a glance. I'm pushing a lot kind of up and to the right, and a little bit down, a little bit to the left. Like I said, okay? But you can take these one at a time in any order. Okay? And see how they're all connected tip to tail like a chain? Okay? And then the tail of the first one and the tip of the last one tells you the resultant, which is the net force. So it's as if there's a single force just pointing that push that way. Is that big? Okay. Right. But no, we're just doing 2 forces. So tip to tail like that. And guys, what would the resultant be for this? 100. Wouldn't that be 100 newtons right there? Okay. I think it would probably be the maximum, wouldn't it? Wouldn't it be the maximum? What if you do this? What if you have 70 newtons to the right? Here's your free body diagram over here. 70 newtons to the right. And 30 newtons to the left. Like that. Okay. Can I add these tip to tail like that? 30 newtons. You guys, what would the resultant be for that situation? It's as if there's a what force acting on it? 40 newtons. You guys see 40 newtons? Right. Do you think that would probably be the minimum that you can get out of those? Yeah, right. Now, you could also go crazy with this. What if you did this 70 newtons to the right and 30 newtons up? Can you connect those tip to tip? 70 newtons, 30 newtons. Okay. You guys, that would make a what shape does that look like on the paper? A right triangle. Can you use Pythagorean theorem to figure out? Here. Yeah, so square root of 70 plus 70 squared plus 30 squared. Get Pythagorean. So this comes out to 76.16 newtons, like that. Okay. Or you could really do any combination, right? Like, what if you have 70 newtons to the right and then 30 newtons off on some weird angle? I mean, that would also be possible, right? Okay. And then tip to tail, that could look like 70 newtons, and then maybe your 30 newtons is off this way, and the resultant is doing something kind of like this. Okay. Probably somewhere between 76 and 100. Do you think the situation here is probably between these two right here? Okay.
Both arrows to the left.
Yeah, you do that too. Okay, so left and left would look just like this one, but to the left. Yeah. Good. Alright. Alright. Alright, let's do number 9 right here. Got a block on the ground initially at rest. 2 forces are exerted on the block, as shown in this drawing. Okay. To move the block in the x direction, what's the minimum external force F1? Express your answer in terms of F1 and this angle of theta, and then draw a diagram and so on. Right? And they're just honed in on the x-axis. They're saying don't worry about the y-axis yet. Okay.
What's the answer for 8?
For 8?
Yeah.
Okay. For 8, this one, the maximum possible force is 100 newtons, and the minimum possible force is 40. Okay, so max min. Okay. And these examples were somewhere in the middle. Okay, so number 9. So give you like some block here, give you an x-axis. X-axis. We got F2, some F2 going to the left. That's F2. And then there's some F1 pulling kind of up and to the right at some angle of theta. Okay. We wanted this to move the block in the positive x direction, which is to the right. Okay. So what's the minimum value of F1 in terms of F2? You guys got that? Okay, so you guys got to break this into components. Say, well, looks like F1 is partially pulling to the right and partially pulling up. Like that. Okay. Guys, what is this component right here equal to? What times what? F1 times
Cosine theta.
cosine theta. Yeah. Right. And for that matter, this would be F1 times sine theta, although the book's not asking for that, but that would be true, right? Now, if you're just focused on the x-axis and there's no other forces going on, and I think you're almost looking at the answer. Isn't it true that F1 cosine theta has to be at least as big as F2, like that? It could be equals for constant velocity to the right, or if it's greater, it would be accelerating to the right. Okay? I think that's what they're looking for. And then if you solve for F1 in terms of F2, guys, how would that look? There's one more algebra step. You go like that. Go like that. Guys, think. Okay. I think that's what the book was looking for. Just that right there. Okay. Guys,
Is that F2 on top of cosine?
yes, because here, guys, do you guys see that F1 cosine theta has to be at least as big as F2? That's the setup. So F1 cosine theta is at least as big as F2. Okay. And then algebraically, if you just divide down cosine theta, you get F1 is at least as big as F2 divided by cosine theta. Okay. So, okay. Now I'm going to do an extension question here. We're gonna put this. We're gonna start with this. We're gonna put this block on a surface. Or well, maybe I should put this block on a surface. Okay. And I'll give this block a mass and a weight, and I'll put some forces in here. Okay. So let's say that I give you the mass of the block is 1 kilogram, which could be your largest lab weight. Okay, so now we're working with this right here. let's say I tell you, here, I'm going to give you the value of F1. Let's do that. Let's say I give you F1 is 2 newtons. And I'll give you Earth gravity is 10 meters per second squared. Okay. And what I want you to find, and I'll walk through this with you guys, is what is the minimum, so could MIN be minimum, coefficient of kinetic friction. Coefficient of kinetic friction, isn't that mu sub k? Okay. So that block is moving at constant velocity. Constant velocity. Okay. Now let's say this F2 is a friction force. So this F2 is a friction force. F sub F R. Okay, like that. Is that what I want to do? Yeah. Let's do that. Okay. Okay. So I just told you guys this F1. Oh, oops. I need to give you an angle. That's what else. Okay. Let's call it 30 degrees. 30 degrees. Okay, so I'll throw that in there too. Okay. All right. So angle is 30 degrees. F1 I'm pulling with 2 newtons of force. Right. And I told you the mass of the block is 1 kilogram. Okay. Guys, if the mass of the block is 1 kilogram, how much does the block weigh? 10 newtons. 10 newtons. Right? Okay. So mg could be 10 newtons. Right? Is that true? Okay. And guys, would there be a normal force holding this block up from the surface?
Yeah.
Okay. Now here's where this gets a little tricky. And this is one of the reasons I want to do this. Guys, would the normal force, show of hands, would the normal force be equal to 10 newtons? Who thinks it would be? Who thinks it's less than 10 newtons? Less than 10 newtons. How do you know it's less than 10 newtons?
Well, you got to pull up a little bit.
Yeah, because this applied force right here, you're already pulling up a little bit. It's sort of like you're alleviating some of the weight from the table, sort of. Right? So I'm going to draw this normal force as less than the weight. Guess how I do that? This does not balance out by itself. Right? But if you throw in this F sine theta, then it would. Okay? Guess I did? Okay, so I give you these values right here. Right, so let's apply these values to the situation and fill in as many numbers as we can, and we'll eventually be able to answer this question. The minimum coefficient of kinetic friction to get a constant velocity. Okay. So I told you a 2 Newton force, but you're pulling at 30 degrees. So guys, how much are you sort of alleviating from the table? Like what is F1 sine theta? Could that be 2 newtons times sine of 30 degrees? Is that true? I mean, it's right here. That's 2 newtons. That's sine of 30 degrees. Who knows what is that?
1.
1. Yeah. Equals 1.0 newtons. Is that true? Yeah. Because sine of 30 degrees is 1/2. Right? Yeah, I'll circle that because that's going to matter. Right. Here's another vertical force, so I'll circle that too. Guys, if you have 10 newtons weight, and you're looking at an angle, so you're sort of pulling up it with 1 newton, which is what that is. What is the normal force actually equal to? 9 newtons. Exactly. That's it. Because for the condition, the sum of the forces vertically have to go to 0. If I write that up, here's your conditions. Sum of forces in the y direction go to 0 newtons. The sum of the forces, and that's because the block is not accelerating up or down. Some of the forces in the x direction is also going to 0 out because that would be the condition for constant velocity. Okay, so this block is going to be in equilibrium. Okay, that all right? Okay, so if we have all the vertical forces and components. I just circled them. Got a 10 Newton weight down. We're kind of pulling upish with 1 Newton, straight vertical. Therefore, the normal force must be 9 newtons. So you got 10 up and 10 down. Sure? Everybody sees that? Okay, now let's go over to F1 cosine theta. So this right here. Did anybody calculate this? What does this come out to?
1.732.
Yeah, 1.732 newtons. Right. So it's sort of like you're pulling to the right with 1.732 newtons. You guys get that? And if that's true, I'll circle that one. If that's true, then how much is the friction force over here equal to? 1.732 newtons. It's got to be the same force, just the opposite way, because that would allow constant velocity, which is this condition right here, constant velocity, which would be equilibrium. You guys get it? Okay. Right. You guys up to here so far? As well? Okay. All right, so, but the question was about coefficient of kinetic friction. So for that, I have to go back to this right here. You guys remember this? Coefficient of friction relates the friction force to the normal force. Now, for the lab you guys did last couple days, this was much simpler. You were just pulling horizontally. So your pulling force matched the friction and the normal force matched the weight. But that's not the case anymore. Okay? But that's okay because we work through the hard parts because we have all the components and I circled all the relevant components. Okay? Got that? Okay. So if we're going to bring in this expression right here in this green box, so you can solve for this coefficient of friction, which I'll do right here. I'll say friction force equals coefficient of kinetic friction times the normal force. Okay, and our ultimate goal is to solve for this mu k. Okay. What number do you plug in for a friction force?
1.73.
1.732 newtons. Okay, so you got 1.732 newtons equals the coefficient of kinetic friction times. And what do you plug in for the normal force? 9 newtons. Aha! Boom! Right there. 9 newtons. Okay. Can you guys solve for mu k now? Coefficient of kinetic friction is just divide over. So that divide by 9. I'm getting 0.19. Hey, that looks fairly similar to the values that you guys were getting out of your lab last few days, doesn't it? Your friction lab. You guys get about 0.2-ish. Yeah. Yeah, so that looks like a pretty reasonable number. Right, you got that? Alright, everybody get there? Boom, boom. Alright, so moving on. Right. So I'm gonna skip a bunch of questions, but I just want to point out that a couple of these look a lot like the puzzle on Friday. You guys remember puzzle on Friday? We're solving like tensions and strings, and they were hanging at angles. Right, that looks a lot like these two. Right, but there's an elevator question here, where I think it's more conceptual. They say, what's the force on between two objects? Right. So skip, skip, skip. I'm gonna skip a bunch of these. And I wanted to hit an Atwood. And the first Atwood looking one is this one right here. Again, the numbers are all wackadoodle. They don't really make any sense. So I don't remember this is. Okay. But you guys see this. Okay. Now, I want to set up my own Atwood first. Some of this like very fundamental, straightforward. Because as I was looking at this, they changed up some things. So we're going to do our own Atwood question here. Right. So you guys ready for Atwood? Here, let's do a new paper. Atwood time. Okay. So say you got a pulley, like a massless frictionless pulley. So that, right, so the pulley itself is not really a factor other than returning the string. Okay. It is like hanging from the ceiling, whatever. And let's throw a couple of weights on here, just like you guys did in your lab last few days. Okay. Right, so how about this mass here? I'll call this mass B. Could be 6.0 kilograms. And I'll have a smaller mass, call this mass A, is 5.0 kilograms. Okay. I guess I put the heavy one on top, so it's gonna accelerate that way. It's gonna accelerate clockwise. Ooh, clockwise this time. Okay, I see clockwise. Okay. So my questions could be, what is the okay. Now I might say the acceleration of the system overall, or sometimes it's phrased this way. Like, what's the downward acceleration of the large block? Because the large block's always going to accelerate down. Okay. So that's one question. Here, let's have a couple of follow-up questions. I wonder, let's make it, what is the tension in the string connecting the blocks? Okay. Connecting the blocks. And how about a third question? So another follow up. Let's do a kinematic connection. Okay. How far does each block move in like some time interval? How about 2.00 seconds? Okay. So let's answer all those. All those. So one at a time. All right, you guys good there? All right. So, big picture here. Everything you need is on this poster, which is thumbnails on the wall. Got it right here. Okay, so if I look at each individual block, I do want to set up some forces. So each block has its own weight pulling straight down and also resisting tension force pulling up. Okay. Now, do you guys see the magnitudes here?
Yeah.
That, guys, the tension force compared to the weights, isn't the tension smaller than the large weight? So that there's a net force pulling the large weight down. But isn't the tension also larger than the small weight? So there's a net force pulling the small block up. Okay. You guys, is it the same tension on both of these? Same tension? Can one string only have one tension? Yeah, as long as it's a massless frictionless pulley, that's going to be the case. Okay. What else? What I want to say about this? Okay, guys. There's two main ways to solve any of these sets of questions that we're trying to answer. Right? Some teachers, some textbooks like to start with each free body diagram and set up a system of equations, which is these two green boxes here. So guys, watch this. In terms of mass 1, it's the tension up minus the weight down. They're subtracting. That would be the net force just on block 1 results in mass times acceleration. Then separately, there's an equation for block 2. It's got its weight pulling down and the tension force pulling the other way, and that results in mass 2 accelerating. Okay? Now you could set up a system of equations, and there'd be two equations, obviously, with two unknowns. You wouldn't know right away the acceleration of the system or the tension in the string. Guys, can you solve two equations, two unknowns? You could do that. And a lot of teachers, a lot of textbooks prefer to do it that way. Okay. How I prefer to do it, I'll do it like probably almost all the time, is what's called a whole system approach. So I look at this from Newton's second law of motion, pink box right here. I look at this as a whole system. I look at these two weights playing like tug of war. You guys see tug of war? Okay. Now, from this point of view, the tension doesn't matter because it's just internal to the system. So only the weights act as external forces, and they're like tug of war. So don't they subtract from each other? So in place of net force, could you subtract? Right? And how much mass is being moved is just, what's the sum of the masses? That's the total inertia. And then you just jump straight to the answer. What's the acceleration? Is that? Okay. That's exactly what I'm going to do. All right. So you guys ready to do that? Ready to do that? And so over here. So first question right here. What's the downward acceleration of the large block? Or I could just solve for acceleration in general. Oh, I gotta label these. Let's label some forces. Okay. Guys, what's this weight right here equal to? 60 newtons. What's this weight right here equal to? 50 newtons? Is that 60 versus 50? Okay. Right, now there is an internal tension, but I'll come back and address that later. So can I say here, F net on M total? So acceleration is, guys, what's the net force? Tug of war style. 60 minus 50? 10 newtons. Acting on how much mass? How many kilograms being moved around? 11. Aha. Okay, so I got 10 newtons net force acting on 11 kilograms, which is 10 on 11. Okay, that's like 0.909. Oh, guys, newtons over kilograms is also called what per what? Meters per second squared. So that's the answer to the first question. The large block is accelerating down that much. The small block is accelerating up that much. But they're both moving the same. They're both tied to the same string. Is that right? Okay, that's question number 1. Knocked out of the way. Okay. Question number 2. What is the tension in the connecting string? I haven't even drawn that yet, but maybe I should go back. Okay. So let's draw a tension that's the same on each block. That's smaller magnitude than 60, but larger magnitude than 50. Maybe it's kind of subtle. I'll call this F sub t. F sub t. Now, if I drew this correctly to scale, this force should be larger than 50. It is. And same over here. Same force, and also smaller. and 60. Right. So all those conditions are true. And so, right? Right. So what is that condition? Right. Now, what I can do is I talked about starting with a system of equations of these two, but really I can just focus on one or the other, and they'll both tell me the same tension. Well, let's try both of them. I guarantee you we're going to get the same tension. Let's try it for the big block first. So in terms of the big block, I can do F net equals MA. There's Newton's second law. And wouldn't the net force be 60 newtons down minus this tension force resisting that? Results in a 6 kilogram block accelerating at 0.909 meters per second squared. Okay, so that's true. Okay. So do a little algebra shuffle, add this, subtract that. Here, save us a little stuff here. 6 times 0.909. Okay. I'm getting therefore the tension force equals 54.5 something. I'll just round it a little bit. So this is rounded a little bit. Okay. So basically 54.5 newtons. Okay. Or I could have said this is in terms of block B. Okay. Let's do it for block A. For block A. Okay. And I'm telling you guys right now, I'm guaranteeing you that it's going to be the exact same tension. Okay. But we'll do a different setup. Let's do the setup right here. You can see right here. So I'm still doing F net equals MA, but now it's for block A. So this is the tension force pulling up minus the 50 newtons weight pulling down results in a 5 kilogram block also accelerating at 0.909 meters per second squared. Is that true? Right, everybody following so far? That makes sense, right? Makes sense? Oh, right there. Okay. Okay. So all I have to do is add over 50. So what is 5 times 0.909 plus 50? Okay. Guys, if you're following, when I hit enter, I better get what on my calculator screen? 54.5 newtons. Oh yeah, it's the same thing. It was always going to be the same. It is every time. Okay. See, same thing. Okay, good. Right. Last follow-up question I asked was, how far does each block move in 2 seconds? Now, one's moving up, one's moving down, but they would be the same distance, right? Yeah. And guys, to answer a question like, how far does something move as a function of time? That sounds like a job for which one of these guys? First one, that's it. Here's how far is a function of time. Oh, can we say it starts at rest? Is that a reasonable assumption? Starts at rest? Right. Oh, that gives us the college equation. Oh yeah, college. Yeah. College. Do some college. So I can say how far it moves is, well, it just boils down to this, 1/2 AT squared. Okay. So how far it moves is 1/2 0.909 meters per second squared. Notice I did not plug in Earth gravity, but the actual acceleration. What did I say, for 2 seconds? 2 seconds? Maybe it's a really, really long string, so we're just letting it go. Maybe it's like hanging from the ceiling or something. What's 1/2 0.909 times 2 squared? I'm looking at 1.8 meters. There you go. About 1.8 meters. Okay, guys. Alright, so back to the puzzles. I want to fit in as much of this last one as I can before you guys take off for lunch here. So we're looking at Atwood here. Now, on the book version, they gave you one of the masses, but not the other, and they gave you the resulting acceleration. So they want you to find the tension of the rope, the mass of block A, and also what's this force from the string hanging from the ceiling. So we're going to do all of that. Right, so this is straight from the book. This is the book Atwood now. Book Atwood. Book Atwood. We got the big block over here. Call this mass A. Got small block here. Call this mass B. Okay. And which is 2 kilograms. Okay, so just copy that straight from the book. And they tell you that it's overall accelerating 3 meters per second squared. Okay, there's enough information there where you can calculate the tension of the rope and also the mass of the block. Now they probably need to find the tension first. That might be a hint that that you can solve that first. So I'm going to draw this weight right here. Okay, guys, what's this weight equal to? How many newtons? 20, because mg. And is the tension up more than or less than that weight? Has to be more than, because it's accelerating up, so the net force is up. So let's do net force results in mass times acceleration. Isn't that Newton's second law of motion? Okay. And the net force, wouldn't that be the difference between the tension pulling up, which we're solving for, and the weight pulling down? Results in mass times acceleration. Okay. So the tension force we're solving for, minus 20 newtons, results in 2 kilograms accelerating up at 3 meters per second squared. Guys, what's 3 times 2? Plus 20? 26 newtons. Okay. So that's a 26 Newton tension in the street. Wait, you guys got that? Okay. Now we can go find mass A. So let's do a similar free body diagram. Now mass A is really big. MA here. Okay. No, it's being pulled back with the same tension, which we just found to be 26 newtons. So I can type a news lift on here. I can say that, but I'm still doing the second law, but now let's apply the first block. Mass A times gravity pulling down minus the tension backwards results in mass A accelerating at acceleration value. Okay, so right here. And so we don't know mass A, which we'll call gravity 10 meters per second squared because we've been doing that. You do know the tension is 26 newtons. That's going to force this mass A, which is 2 kilo. Sorry, we don't know mass A. We're solving for that again. Okay, to accelerate at 3 meters per second squared. So add this, subtract that. Guys, what's 10 minus 3? 7 times mass A results in 26 newtons. Okay, divide both sides by 7. Okay. So mass A equals 3.71 kilograms. Wait, yeah, it is the heavier the block. It always had to be the heavier one, and in fact it is because it's more than the 2 kilograms. Okay, so here's what we do. My earlier class, I was able to answer one more question. I'll set it up with you guys. There's one more tension. You guys see the string hanging from the ceiling? You guys see the string hanging from the ceiling? They want you to find the tension in the string. Here, guys, do you guys think the tension in the string is equal to the weights? It would if it was at rest, but it's not at rest. It's accelerating. So it's actually alleviated a little bit. Now, here's what I'm going to do. When the bell rings, you guys take off for lunch. I'm going to record this while you guys are walking down the hall for lunch, and I'll put that in the video, okay? So I'll show you guys how to calculate the tension in the string where it's hanging from the ceiling. Alright, so pause this video, let the bell ring. Alright, you guys have a good lunch. Alright, and we're back here. So we're going to finish this out. What's the tension in the string was the last question. So picking up from here, I just found the mass is 3.7 kilograms, this mass A. Therefore, this weight right here, I know must be, M times G is 37.1 newtons. Okay? And I can play off that or do something with that. Right? Or for comparison. And so I'm going to take this pulley up here and blow this up. Look at this. Okay? So yes, it has a string where it's attached to the ceiling, or maybe the other day you were holding it in place. I wonder what tension you would have felt. Okay? Again, if you had held this at rest, then it would feel like the weight, which is 37 plus 20. It would feel like 57 newtons holding it at rest. But this is not at rest, so it's actually going to be less than 57 newtons. Okay. What it ends up being is, here, if I just call this a FT ceiling, okay, and maybe this is like FT string. And so this is FT string pulling here and also pulling down this way. So this is our regular FT, which we found before. We found that to be 26 newtons. So this is 26 newtons here. This is 26 newtons here. But if the sum of the forces in the y direction is 0, right? Because this pulley isn't moving up or down, it's just sitting stationary in place. That means that FT ceiling minus 26 goes to 0. Or it'd be 26 plus 26. FT ceiling equals 52 newtons. Now I said that should be less than the actual combined weight as long as these are accelerating in motion. Okay? And what was that again? 37 plus 20. Yeah, it sure is. So 52 newtons is indeed less than 57 newtons. So if you're holding it at rest, it feels like 57 newtons. Like you're holding up the whole thing. If you let it go, right, then it's sort of in free fall, right? Like the small block's moving up, the large block's moving down, but the overall center of mass is moving down. Right? And so you're sort of alleviating some of the tension up here. Right? And it jumps down from 57 to 52 newtons.